here to present Phyllis Stabeno, scientist from PMEL, and she's presenting on causes and implications of record low sea ice extent in the Bering Sea in 2018.
Thank you. What I'm going to present today is a combination of work or integration of work from other scientists at EcoFoci and other scientists in NOAA. So the Bering Sea, The Bering Sea is the third largest semi-enclosed sea. It's largely divided half between a shallow shelf in the east and a deep basin in the west. It is large. California easily fits on the eastern shelf, and you could squeeze Washington and Oregon in if you're willing to kind of chop them up a bit. It's the home to vast numbers of marine mammals and birds. It produces 40% of the U.S. catch of fish and shellfish by weight, worth off the ship over $1 billion. And in addition, it's a unique area. It provides 3/4 of the sustainable or the subsistence harvest that's for the people who live along the coast, who have lived there for thousands of years. But what defines the Bering Sea is sea ice. Shown here is one of the better images of sea ice. Over here in the, on the left, you can see the winds. These are windrows as it comes off the ice. This is the direction of wind. Down through the central, this darker, chunkier area, this is thicker ice. Ice can be 20 meters thick on this shelf or deeper. The wind blows, it pushes it down, and it pushes it toward the edge. In these darker areas along the coast, those are polynyas. The ice blows there, it pushes the ice further on, and it leaves open water. And that water is very cold, minus 1.74. And the wind is cold, so it quickly freezes. And what's interesting in this image is you can see how long these dark areas are. This is all thin ice, newly formed ice in these polynyas. You can see them all along the coast, here at St. Matthew and at St. Lawrence. The leading edge, you can see the little tendrils of ice that bands of it move a bit faster because it's either taller or differently shaped, and it goes out into the water, balmy 3 degrees, and it melts. So this is what we've seen in recent years. On the left is 2012. This is not as clear an image as the other one. It has a lot of clouds. You can see the windrows here in the south. The wind is blowing almost due out of the north. The thicker ice here in the central. But the basic thing is on April 1st of 2012, the Bering Sea shelf was covered in ice. 7 years later, just one day earlier, on 31 March, there was basically no ice on the northern Bering Sea shelf. There's a few areas you can see. There's a little bit of ice right in here. There's some ice over in Russian waters over in here. And in a few of these areas, there's some ice, right? But on the whole, there was no ice. In addition, the southern Chukchi also was ice-free. 5 years ago,
So people online just asked if you could describe a little more the areas.
Sorry. So the Chukchi Sea is here at the north. You can see Russia, Siberia on one side, and they come pretty close at Bering Strait. And so north of Russia, all this blue water, that's ice-free. Most of the smooth-looking clouds, the non-chunky clouds, white, those are all clouds. But this is unheard of just 5 years ago. The Chukchi would be ice covered into June. And so this is a big change to this system. Similarly, the northern Bering Sea would be ice covered. So let's look at this in a different way. Just look at the variability we see on this. On the left are the time series. It goes from 0 to 1,000,000 square kilometers. This is the area of ice on the eastern shelf. And when you look at it, you can see a lot of variability. The blue line is 2012, the highest ice extent we've ever seen. And these records go back to 1979, the high quality ones. And on the right side, you can see how far 2012, how far the ice came out into the basin. And now comes the recent 2 years in red. The solid line is 2018. It never reached above about 0.4 or 400,000 square kilometers. And the next year, in 2018-19, that ice year, there's higher ice early on in January, but it also decreased, and it became very similar to what we saw in 18. Shown on the right are the lines of it. You can see 2018 had very low ice, nothing in the middle part or that area deeper than 50 meters. 2019, because of this high ice in January, it was a bit more extensive. Maximum ice extent typically occurs in late March. You can see it, the black line on the left is the average over all these years, and it happens late March. You can see that these particular examples, there were 2 examples that were in January. One was this year and one was in 1989. But on the whole, it's late January that you get maximum ice extent. What causes the variability in ice extent? You can have 1,000,000 square kilometers of ice, or you can have less than half of that. And there's 3 things that really matter. One is ice, or one is the winds and the temperature, the air temperature of the winds. The second is the length of the ice season. If you only have an ice season that's a month long, it's not going to push ice as far south as if you have 6 months of ice. And then ocean temperatures that the ice is coming over, because the leading edge will melt and cool the water column. If it's warm enough, it can delay ice. It can't prevent it from coming south, but it can delay it. So let's look at these 3 items. Shown here is the average ice extent on the top here. Is the average ice extent from 1980 to 2015. It's color coded. You can see here, dark blue is open water, white is a lot of ice. Below the December ones is the winds. And these are the radial histograms. And what you can see is in gray, what percentage of the time are the winds out of the northeast going toward the southwest? And it's over 60% of the time. In other months, it could be 70%. This is the direction of winds in the winter in the Bering Sea. And that pushes the ice south. In addition, the temperatures typically are cold. Here in December, you can see temperatures were about -5 to -10. A little bit later, in January, -10 to -15 or colder. So this is what makes the ice. You need both winds in the right direction and very cold temperatures. So once again, we'll return to this, and we want to look at what happened in 2017 and 18. And we're going, part of our focus in this time will be at M8, shown on the map here. We have a long-term mooring that was first deployed in 2005, and it provides us a lot of insight in what happened. So the top part is, once again, the ice. The second is the winds at M8. And then the next one down is the wind anomalies. And what you can see in the wind anomalies, that they were very much out of the south and toward the north. The second thing for 2017 and 18 at the bottom, the red line is the air temperature in 17 and 18. The black line is the long-term average. And you can see it was 10 to 15 degrees warmer. Warm air does not make ice very rapidly. It also doesn't make very thick ice. So let's look at the various events that happened here. I pulled off just the 2017-18 ice and the mean, and shown below is the winds. Upward is winds are toward the north. And so the first period in November had winds toward the north. There wasn't a lot of ice at this time, but you usually begin to form ice in November. But there wasn't a lot of it, so it didn't really make the ice retreat. It just failed to have it advance and be formed. The other thing is, like I said before, the temperatures were above zero, which was highly unusual. If we move over a little bit and look at December and January, here the winds are out of the north. As is typical at this time, you can see the histograms on the right. This is typical, but the temperatures, the air temperatures were still 5 to 10 degrees too warm. Not really strong. It can form ice, but not as well as much colder temperatures. Finally, we go to February and March, and this is truly an unusual time. And what you see are the winds of the north. If you look at the blue line on the top here, you can see the ice retreating down to about 200,000 square kilometers. The winds turn around a little bit here in the middle. The ice advances a little bit, and then they turn again. What happens next in April? April can also push ice south, but by this time there has been no ice on the southern shelf. The temperatures are 2 degrees, and that's just too warm this late in the year for you to advance ice very far south. So you get a little bit of an advance in late March, but that's it. The ice season is over, temperatures become warm, the winds come out of the south more, and that's the end of the ice year. This is another way of looking at the same data. Once again, this is the aerial ice extent. These are by monthly means. So orange is March and April is green. And what you see from 79 up to about 2013 or 14, a lot of variability. There's big ice years, low ice years, and it varies. But there's a fairly constant amount of ice if you put a mean through it. Then, toward the end, you begin to get a lower amount of ice, and certainly 18 and 19 at the end, the ice is way down. What caused that? We saw that it's winds primarily that cause this ice extent. And when you have winds out of the south, and it takes about a month long, a 31-day time period for the ice to retreat, for you to reforce it. So we took all the data from NAR from 1980 to the present and ran a 31-day running mean on it. So we ended up with 31-day periods to see, when do we get winds out of the south? How often does that happen in the ice forming months, which is November through March? And we got a bunch of points. I kind of thought they would be just randomly scattered. They weren't. If, for instance, December 16th, which would have been the average of the month of December, had winds out of the south, it was likely that the next day, the average from December 2nd to January 1st. And what happened is all of these periods, these 31-day periods with winds out of the south, clumped together in 13 periods. And you didn't see a month-long period or a 31-day period of winds out of the south in any other time. And those periods are shown in the dashed lines. The first one occurred in 1989. From 1980 to 89, it never happened. Then, 5 months later, and the months or the letters at the bottom are the center of that period. So The 89 one was primarily in February, the time was. January, 4 years later, there was one in January, November. Anyway, you have a real spread of these things. In 2004, there were 2 events, one in November and one in December. And then we get to 2017 here. We had 2 of these events of winds out of the south, warm winds out of the south. The next one was 2017 and 18. And ice seasons, the months are all in, for instance, in 18, so that means November and December of 17 contributed to that ice year. But anyway, 17 and 18 had 2 strong events, and 2019 had 1 strong event. The 3 strongest events here were the 17-18, the 18-19, and interestingly enough, the 1980-89 was also an extremely long, persistent event of winds out of the south. So we're seeing a change here. This is not a random occurrence of these winds out of the north or out of the south. So why could this be happening? This is some work by Al Herman that he is now, I think, in press. What he was the models. How often do you see, or where are the wind directions in this region? And if you look at the plot on the left, is you in both directions, but the whole beginning in 2040, 2050 there, you're getting an increase of winds out of the south. Other models, other climate models show the same pattern, that in the long run, we're going to have more winds out of the south. The problem is we're not in 2040 or 2050. We're in 2020. And so the question is, has the future arrived early? And I don't know. One of the interesting parts is the biggest ice year we had was in 2012. And the least ice year was 6 years later in 2018. So we're certainly not seeing the steady decrease in ice. There's immense variability in this system. And are we just seeing extreme randomness, or are we actually hit a tipping point? And I don't know. So let's look at the next thing. This is duration of ice. Like I say, you need for the ice season to be long enough to push the ice 1,000 kilometers south over the Bering Sea shelf. So once again, we'll look at M8, which is shown here. And these are the different patterns. The day of arrival in a 50 kilometer by 50 kilometer box around M8. On average, it's December 29th. Day of retreat. When does the ice fall below 20%? May 16th, and then the duration. You have 141 days on average of ice at this location. And there is no trend through 2014. There's a lot of variability in these time series, up and down, but there's no trend until 2015. Once you begin to add these later events in, you're now beginning to get a significant trend. So why is this happening? And one possibility is if we look to the north of the Bering Sea at the Chukchi Sea, outlined in orange. It has, the day of ice arrival has become later and later by about a day on average. The trend is about a day a year that's arriving later. The Chukchi has to freeze before the Bering Sea can. If the Bering Sea, or if the Chukchi is open, has no ice over it, it's letting heat into the atmosphere. Therefore, the winds are warmer and they're not effective are as effective in making ice as they could be. So what's happened is this. The pink line, dotted line, is the flat line average of when ice arrives at M8. And the black dashed line is the trend for the Chukchi. As you can see, they've now intersected. So since the Chukchi is being forced by larger dynamics, it could be playing a role in delaying the arrival of ice in the north at M8. The final item was ocean temperature. And the warmer the ocean is, the more it delays the ice. This is a mooring in the very southern part, which is fairly representative of the whole southern Bering Sea shelf. It's a 25-year record. And the top line, or the top plot, is ice. How much ice is there in March and April? And what you can see is up until 2000, there's a lot of year-to-year variability. At 2000 to 2005, there was virtually no ice at this mooring site. And you can see the average. This is depth average temperature. And you can see how warm the temperature is. The depth average temperature in August reached 8 degrees, which is a remarkable temperature for the Bering Sea. Then we had another period of very extensive ice, and the temperatures are very cold. If you look at it, you can see that the maximum temperatures, like in 2012, was basically the same temperature as the minimum temperature in some of the low ice warm years. So one of the places here that you can look at is 2005. It's very high temperature here. 2006, the winds were strongly out of the north, and we should have gotten quite a bit of ice. But we didn't get as much as expected because all of this heat had to disappear, and it slowed down the advance of ice. So this is the physics, or how the ice works. So how does ice influence the whole ecosystem? And I'll be looking at the temperature of the ocean, nutrients and primary production, zooplankton, fish, marine mammals, and humans. So let's just start with the physics, how the water column is structured. Once again, I'm looking at M8, the red dot up here. Shown on the left is the average temperatures from 2005 to 2017 at this mooring site. And what you see, and on the top of that plot is the ice. So during the ice forms here, you see it in November, the water column cools, you go around to January, it increases, temperatures become minus 1.73 throughout the water column. The ice begins to disappear here in May, and it has nowhere to go, it melts. And that means it puts a lot of fresh water into the surface of the water column. This lens of fresh water allows the surface to warm up, and it can get up to 12 degrees, which is pretty good. But the bottom here stays cold. This lens of warm, fresh water on the top insulates the bottom, and it keeps it cold. And it keeps it cold for the whole summer. And when this water is less than 2 degrees, it's called the cold pool. Shown in the upper right, is the cold pool for 2013. It covered almost the whole shelf. Cold pools are important to this system. It provides a barrier for a subarctic species of fish like pollock. They really prefer their water warmer than 2 degrees, so they tend to avoid it. Provides a refuge for young pollock. Young pollock aren't as particular. They're quite happy being in there. And since their adult pollock have the nasty habit of eating their children, it's a good place for them to be. And it provides a corridor. All the species in the north want to come south for more food, and they can go down this cold water corridor. shown where lab did, and what you're looking at is the ice or the cold pool extent over from 2001 through 2018. You can see every year there's a fairly extensive cold pool until you get down here to 2018. Very, very small. Some people have begun to call it sarcastically the cold pond or the cold puddle because it's very small. Once again, some work by Al Herman on the right. The dashed line shows what the predictions for 2050 were in the climate models. This is what the cold pool size would be. So what we saw in 18, and I suspect we'll see in 19, is a cold pool that is similar to what is predicted about 30 years in the future, 40. Okay, so let's look a little bit more detail of the cold pool. Once again, we're at the mooring M8, which is in the northern Bering Sea. On the right, the red line is the mean from 2005, that should be, through 2017. And the blue line is what happened in 17 and 18. You see two things you can see here. One is the temperatures are much warmer, and the second is you see warming starting in April, and this temperature here was below 2 degrees, so it was a cold pool, but in August it went above the 2-degree mark. You go a little bit further south, there's another long-term mooring here at M5, just south of St. Matt's, the same pattern of red and blue, and you can see its temperatures were warmer. There was even less ice there, and the cold pool disappeared in April at that location. So let's look at the anomalies here. They're a little bit easier to see what kind of changes we have. So you just subtract the mean from the 17-18 record, and you get this. These are the anomalies. And we're going to just focus on M8. And the first thing is you can see from November through kind of April, it's pretty flat. And the reason is there's usually ice over this at that time. There's certainly no heat coming from the atmosphere, so the temperatures are pretty constant. And under the ice, they would have been minus 1.74, so you're not seeing a lot of change there. But the next one is what fascinated me, is why did the bottom cold pool warm up? That is something that doesn't happen, because it's been insulated. And after you've thought about it, the answer is salinity. When the ice melts, it introduces immense amounts of low salinity water. That helps to stratify. Half the stratification at M8 is due to salinity, and half is due to temperature. And so the long-term average salinities at 30 meters and 55 meters, you can see above. Basically December through April is all well mixed, and then you begin to see the freshening of the surface. The problem is the 30-meter one is not in the surface mix layer. The reason is because we've seen 22 and 23-meter ice flows there, and they wipe out your mooring. We lost one mooring when we were stupid and put something at 15 meters. And so what we're seeing is this water coming down, this freshening coming down from the surface layer. The bottom line shows what happened in last year, or in 18. The system remained mixed. There was no fresh water. So this density structure, vertical density structure, was very weak. And it easily had these storms, weak storms would come by, mix some heat down, mix some nutrients up, and slowly the bottom layer began to cool, and we lost the cold pool. So you can ask, well, what about this year? These moorings are still in the water and will be there until, hopefully, August. But we had a cruise this year in late April, and it went fairly well. Once again, here's the Bering Sea, here's St. Matthew, this upper left panel, temperatures, you can see bottom temperatures as you go north. This is Dyson, traveled north. Dyson got to the northern part of St. Matt's. The weather further north was dreadful. And so they deployed this light pale green thing, which is an oculus. It's a glider, and it goes up and down in the water column. It's designed for the shelf. It goes up and down 3 times in a kilometer, so you get really dense data, and it's continued north. Last time I heard, bottom temperatures were -1 degree approximately. A little bit colder than they were last year in 18, but still well above the average of what we expect. Let's move on to nutrients. Nutrients are the fertilizer of the sea. 2 things we're looking at here are silicic acid, silicate, and nitrate. This is some work of Calvin Morty's, and usually what we do is this line, the 70-meter isobath line shown on the map. It's been done every year for about 15 years, and the red dots are what we did in 2018. Shown to the right, first is salinity. The salinity was high because there was no melting of ice, and so there was no fresh water. But the surprising part were both silicic acid and nitrate. Both of them were at the upper limits of what we've seen before in this. And we've been discussing this. Calvin will put out a hypothesis of this is why. And someone will come along and say, no, because of this. And so far, we have not figured out why we have such high nutrients in 2018. The interesting part is the Chukchi Sea saw the same pattern. In the Chukchi Sea, the nitrate was over twice the historical average. So we have very, very high nutrients in these years. Nutrients feed the chlorophyll. There's kind of 2 types of chlorophyll on the northern Bering Sea, or in the Chukchi for that matter. There's the chlorophyll that's right underneath the ice, shown in the cartoon at the bottom. This is ice algae. Certain types of zooplankton prefer ice algae. This ice algae resides under the ice melts. It no longer has a structure, and it falls to the bottom. It then feeds the crabs, the clams, everything on the bottom needs this input of chlorophyll. That they in turn feed the walrus and the bottom feeding whales. Shown on the right here, this is actually a plot in the Chukchi, but the northern Bering has the same look. You can see 2 blooms here. You see a very weak bloom at about 18 meters, high chlorophyll or fluorescence. To the right is the plot or the picture of what it looks like. It's kind of a green, cloudy type stuff. That's probably phytoplankton. However, down deeper, you see a very strong bloom. The picture over here is really granular. It has a lot of lumps in it. This is ice algae. And so that is what falls to the bottom, and that's what we see here. Of course, in 2018, there was no ice algae in the Bering Sea. In the northern Bering Sea, most of it. So why is this timing important? This is once again the southern Bering Sea. And if in the southern Bering Sea, in the center plot, if you have ice in March, or even early April, you end up with a bloom underneath the ice. It's the ice algae. That ice algae will consume the nutrients, and so there usually won't be a phytoplankton bloom. If, on the other hand, you don't have ice algae, you don't get a bloom until May, when this water column stratifies. We're trying to improve these measurements to get a better feel for them, because these were all a single instrument on the mooring. And we're now beginning to deploy the prowler, which continuously measures. It has a prowling instrument that goes up and down multiple times an hour, just measuring the water column. So it gives us a better idea rather than just a line across here. You can see the shape of the chlorophyll bloom. This is at M2, the mixing on the temperature, the enhanced chlorophyll here with this mixing event, etc. On the northern Bering Sea, however, it was a little bit different. Up until 2018, we only had ice algae blooms. Shown here is ice retreat. So if the ice retreats on the day 120, you're here, and then the maximum bloom, the day of maximum bloom. So the ice retreats, the ice algae falls down, it falls past the fluorometer, and it registers, and it says, yep, we're here, and you're seeing that bloom. And so the timing is always related to when the ice retreats. 2018, that was not so. You can see it here in red. Here's the time series from the mooring. You look through October, a little bit of something might have happened here in October, a fall bloom perhaps, but through May, there was no production. That means there was no ice algae at that location. A beautiful bloom here, phytoplankton bloom, a little bit continuing later in the year as you mix up nutrients, and that occurred in June maximum. So we've shifted from this, and so the benthic communities did not get their food this year. We move on to zooplankton, which I view as the great mystery of the ocean, and this has been explained to me many times, so if I screw it up, it's my fault. This is at M2, once again, the southern mooring. When you have low ice shears, you get a lot of small zooplankton, which is the green. On cold years with a lot of ice, the number of small zooplankton disappear, and a number of large zooplankton increase. Small zooplankton are celery. They don't have a lot of lipids in them. Yeah, they're good for you and me, but it's questionable how good they are for the fish, especially the young. The big zooplankton have immense amounts of lipids. And young of the year pollock or other fish need to eat it. At the end of the summer, they need to be fat so that they can make it through the summer. And they need large zooplankton to be fat. So what happened in 18? These are once again the anomalies on the left, northern Bering, southern Bering Sea, and this is for small copepods. And you can see how many small copepods there were. Biggest numbers we've seen. So there's an immense amount of this might be related to how much nutrients we had in the system and the late phytoplankton bloom, but it's still being investigated. Large zooplankton or copepods, once again, the northern Bering, the number was way down. So, and in the south, it was also way down, but you saw these real low numbers in the north. If you look at just a map of them, this is the 2018 cruise, and what you're seeing is the north and the south look a lot alike. Amount of small and large zooplankton, the ratios are very similar, which is unusual. Okay, let's move on to the Walleye Pollock situation. Once again, the kind of orangey red thing here is the cold pool, and you can see in 2010, 2017, and 2018. The yellow or the purple here is concentration of Walleye Pollock. Pollock don't like the cold pool, so you see them highly concentrated along the outside edge or around it. This makes it easy for fishermen to find them because they're very clumped together, so they can go out and catch them fairly easily. 2018, no. They're spread out. You can see the two biggest clumps are over here. This is the US-Russian border thing, and you see them in the north. The ones in the north, pollock are mainly feed in the pelagic zooplankton. A lot of those pollock had been eating off the bottom. They had bottom creatures in them. Benthic communities are slow to heal, and having a large population of pollock up there could have damaged, and that needs to be looked at. The problem over here in 2018 at the slope is there's a lot of pollock there, but there was also the Russian pollock fleet was up here too, and a lot of those pollock probably went visiting and may not have returned. So I apologize for the last plot. We didn't have it in this thing. This is Bob Loft's work, by the way. Pacific cod, peacod have a similar pattern, except even more so, where you saw just in 18, all of the peacod were in the north. Okay. Birds. This is some work by Kathy Kulitz. There wasn't a massive die-off of birds, but there was a die-off of birds. The birds did not do well, and they haven't for the last couple years. They have looked at them. There's evidence of starvation. The harmful algal bloom toxins are still being investigated. But the unusual part is how spread out. Usually you get high death rates in small locations, but this was spread out over the shelf. This is some work by Catherine Burchak, shown in the upper right in the map is the locations of all of her moorings. And she has passive acoustics. She's listening to all the marine mammals. I just wanted to show you one of them. This is the Bowhead Whale. Bowheads winter in the Bering Sea, go to the Chukchi in the summer, get fat by eating everything, and come back. In 2017, this is the southern Chukchi, this is the northern Bering, the two lines. The southern Chukchi, you can see very high, solid concentrations. The black means you heard a whale every 10 minutes for the whole day when it goes all the way. So it's the percent of time you hear it. And so the black you can see early on. The blue line is ice, and you can see that the bowheads would disappear when the ice got heavy and thick. In 2018, for the first time, there's evidence they overwintered in the Chukchi Sea. The Bering Sea plot data was just analyzed down here in the lower right. It shows a very similar pattern. There were bowheads the whole time under the ice in the whole southern shelf. So there's been a northward movement of these guys. Okay, so this is the fur seals. And fur seals breed or pup on the Pribilof Islands. Used to be about 80% of the fur seals of the world, northern fur seals, would pup there. It's now down to about 50%. It's been decreasing regularly. This happens to be a plot that is in Morty et al. And it was a sail drone, and it was following along the fur seal, and this is what it was looking at. It was looking at what was in the water with an echo sounder. And you can see when the fur seal dives deep, that's what we're looking at, how depth it is. There's a lot of food down here. When it dove shallow, there's more food in the surface. So, what about fur seals? Shown on the left, this is some work by Kathy and Jeremy, is the number of fur seals, pups, has been going down regularly. And up until 84, they hunted them, and so that big decrease early, but we've seen kind of continuation of this decrease. So let's look at 2 years. They put cameras on these fur seals, okay? And let's look at 2 years, 2017 and 18, because that's the 2 years they had the cameras. And in 17, you can see there was a lot of pollock. The purple, once again, was all around the Pribilof Islands in the blue circle. In 2018, there were virtually no pollock observed there. So I'd like to show two movies. Go ahead. One for the first part, 2017, when there's a lot of pollock, and one in 2018 when there wasn't. So what you're going to see is so here you can see the head of the fur seal diving down, looking for something to eat. It's a she, by the way. She's going to need this to feed her pups. And that was a pollock. So she succeeded. Pollock isn't happy, but the pups will be happy because she can feed them. So let's look the next year. There's not very many pollock around the Pribilos. That is a salmon. And here our fur seal is chasing that salmon. Who are you rooting for? Going along, makes a couple grabs for it. No, didn't get it. Oops. And she has to give up. She's run out of air. She spent a lot of energy going after that salmon. Salmon are much harder to catch than pollock. And so this is the changing system we're seeing in this, that what happens kind of influences the whole ecosystem. You know, loss of ice just doesn't affect the temperature, but it goes through the whole ecosystem, and that's what we're looking at. The next one are people. There are many native communities along the Bering Sea coast. They've lived here for thousands of years. They depend on the ice to move, to fish, to catch their whales, to catch their walrus, you name it, to protect them. Ice is a glorious thing. If you get seasick, like I do, and you go out there and the weather is dreadful and the water is dreadful, you go into the ice and it just damps it out. The winds are still there, but you feel much, or at least I feel much better. The same thing happens up here. And what happened is you can see these big waves. There was a lot of infrastructure damage because there was no ice to dampen this out. In addition, you can see what shown here. This is outlook, walrus outlook, and below. This is what it's supposed to look like. It's supposed to be covered in thick ice. You can run your snowmobiles on it. You can walk. You can fish. You can catch walrus or whales and pull it up. But this is what they had in 2019, right below it. This is not what they were happy to see. In addition, shown over here, these are the hunters. You can see here, excuse me, a drone going out to look at things. It's now dangerous often to go on the ice. There have been people who have fallen through, and the question is, what is happening? Is this going to change? Where are we? And whether we're going to change or not, as I told you, 2012 was the biggest ice year we had, and 18 and 19 were the two lowest. So it's hard to say. In the long run, we're going to lose ice. But is it going to be immediate or on a longer scale? It's hard to predict. Almost all my predictions, by the way, are wrong. So I've decided to give up on them. So, yeah, this is just kind of the summary. Yeah, you can read it better than I can. So are there any questions?
And just because we're running low on time, I'd like to take some of the online questions first. If need be, we can continue offline. So. So we have someone who asked, does the wind and air temperature data at these moorings be made available in real time via the GTS or to the Weather Forecast Office?
Because of the ice, we once put a surface mooring in the ice and it wiped it out, everything. So it's not available during the winter in real time. We are working, to make the southern mooring, which is a surface mooring in the summer, available in real time, which would add. So that's a goal we have. In the past, the Weather Service hasn't really been interested in a temporary mooring. It's not there year round. It was there for 5 months. So it's something we need to work on.
Okay, great. And then another question we had, we are seeing a major spike in gray whale strandings on the west coast, the most since 2000. Since gray whales are known to reflect conditions in the Arctic, and many of these whales have been skinny or malnourished, would these conditions last summer have affected the whales feeding in the Arctic? Do you see a connection?
I'm a physical oceanographer, and I can see a connection with anything. But my colleagues in marine mammals will probably kick me if I say very much. I do not know. They should talk to someone like Catherine Burchalk or one of those people at the Marine Mammal Lab, and they could give them a much better answer, informed answer than I could.
Okay, great. Someone else wanted to know, are other Arctic or subarctic ecosystems experiencing similar trends, or is the Bering Sea unique?
No, the Bering Sea is not unique. The whole Arctic is losing ice. There's a steady decrease in the in the amount of ice in the Bering Sea, or in the whole Arctic, and so the system is changing. The Arctic is warming. It's the place that's most sensitive in a lot of ways to climate change, and so you're seeing a loss of ice throughout the whole Arctic.
Thank you. Someone else asked, do you have information on the impact of low phytoplankton and benthic amphipods, which is gray whale food? We're seeing a lot of malnourished gray whales. So that's another.
Yeah, Catherine Burchalk.
And then someone wanted to know the maximum depth of the oculus used as it goes up and down.
That oculus, it can go as deep as 200 meters, but it's on the shallow shelf and it goes to about 70 meters. So yeah, it's a really nice instrument. It gives us measurements in a place it's hard to get to.
Okay, great. And we'll do one last online question for now. Does the wind and air temperature data at these moorings be, oh, we already did that one, sorry. Are the observed northern and southern cold pools in 2002 considered anomalies, or do they occur more regularly?
The cold pool is related to how much ice you have in the south. And so if you want a cold pool south of St. Matthews, which is about 60 north, you have to have ice. And so if you have ice down there, you get a cold pool. It shrinks as you go through the summer, except in that middle area where you have a two-layer system that can cap the top part and keep, it's a cap at the top and it keeps the bottom cold.
Are there any questions in the room?
In regards to, I work more on the policy side of things, and our team is curious on, how these changes will necessitate new policies or new access to fishing grounds. I'm remembering back to the map of the pollock and everything moving north into Russia. Has your team been in touch with anything regarding policy changes needed?
Not so much policy, but I'm working with Chris Wilson, and what we're doing, I'm doing the physics, he's doing all the hard parts, is we're putting an array of active acoustics along the US-Russian border, and we want to see how many pollock are actually going over that line and how many are coming back. And so it will go to a depth of 100 meters, which is the edge of the shelf, and he thinks that's how the pathway that they would take to the north. And so that will go out, we hope, in July and August, and we will then recover it next July and August of 2020, and we'll see what kind of patterns we have. What we do know is there was a lot of fishing boats in Russian waters last year, and we know that the pollock were probably there, that the water was just warm enough and they just went further north.
Question about the link between the wind direction and the air temperature. You mentioned that air temperature is much warmer later in the season when normally be a lot colder, like a 28 period. How much of that is like a feedback loop?
that,
Could you repeat the question?
oh, sure. She's asking how much of the warmer temperatures we saw in 18 that would have been in February and March was due, air temperatures was due to a feedback. And that air was coming out of the northeast, and that had solid ice up there. And it was warmer, and I don't think it was as much a feedback as the weather patterns, the patterns of the lows and things. You can get warmer air from further south, and it comes back around and then comes over the Bering Sea, and that air is warmer than if it just comes from the North Pole.
Any other questions in the room?
I know you said you're not in the prediction business anymore, but do you see profound changes to the ecosystem here if these trends continue with the whole ecosystem as we know it?
What we have seen is in 2001 to 2005, which were very warm years, low ice year, management cut the pollock fishery almost in half because no pollock were surviving, or very few pollock were surviving for a 5, 6, 7 year period. And it takes about 3 years for pollock to recruit to the fishery. And they started for 3 years in a row, they cut the pollock fishery. The interesting part is the fishermen did not disagree with that, because this type of information I gave here is presented regularly any place we can present it, and they knew what was happening. And we also were entering a cold period, which everybody figured the pollock would come back. So there was no huge complaints when that, and that was a big cut. Pollock is a big fishery up there. So yeah, I see pollock having problems. This is changing an ecosystem. I mean, ice is what has shaped this ecosystem for thousands of years. And we're going to lose it. Maybe not next 2-3 years, but in the next 10, 20 years. And that is going to change the ecosystem. There's not going to be ice algae. You can go down the list of what's not going to be there. There's going to be winners and there's going to be losers. And you might be able to predict some of the losers because you know they're not going to manage well. It's real hard to predict who the winners will be, because to me, ecosystems are a bit of a gamble. You don't know quite where the ball is going to settle to see what ecosystem you're going to end up with and who's going to do really well.
Okay, we have one more online question. Will the decrease in stratification due to loss of sea ice impact the timing of the spring zooplankton bloom?
That's a good question. I think it will impact it in one sense, in that you certainly aren't going to have any of the real early ice algae blooms. But my suspicion is that the fall or the spring bloom will continue to be in that May time period. Although, if the weather patterns, the wind patterns change, it could become earlier or later depending on mixing, because you need a stratified water column to begin a bloom, because you can't mix the phytoplankton way down because they don't get enough light. They want to stay in the upper 20 or so meters.
Well, thank you everyone for joining us, and thank you, Phyllis.
Thank you.